The division properties of radicals, that's the next rule, where it says in order for us to divide radicals, similar to the multiplication property, you have to have a common index. The radicands do not have to be the same. So what this property is saying here is that we can take the square root of, or the nth root of a over b. You see the fraction, and we can write the radicand, this fractional radicand, as two separate fractions, the nth root of a all over the nth root of b, or vice versa. Where you see the two separate radicals as fractions, we can write the radicand as just one radicand. So with example 4, we have the square root of 15 all over the square root of 5. We have a common index, which is 2. So what we can do is take the 15, the radicand of 15, and the radicand of 5, and we can make it into one fraction that has a common radical. And then we can divide 15 by 5. That gives us the square root of 3. Next example, number 5, we have the square root of 7 over the square root of 9. So this time we have the one fraction. And we see that 9 cannot divide into 7. So what we're going to do is write the radicand as two separate fractions. The square root of 7 over the square root of 9. And then let's look and see if we can simplify the numerator and or the denominator. Well, the square root of 7. 7 is not a perfect square. We will keep the square root of 7 in the numerator. But the denominator, the square root of 9, we can take the square root of 9 because 9 is a perfect square number, and that is 3. Now, one rule that I'm going to make note as we are simplifying with fractions, simplifying radicals in fraction form, you cannot have a radical in the denominator. Just like whenever we have a fraction such as 4/12 that can be reduced, well, or simplified, and we know 4/12 reduces to 1/3. Well, we cannot have radicals in the denominator. We have to simplify it. Now, what in this section we're going to be looking at radicals that can be simplified in the denominator, but later on in the chapters we will be looking at what must we do when the denominator is not a perfect square and it can't be simplified. So but for right now, I think using just learning this property, you're able to go ahead and simplify that denominator. Let's do some more examples. We have number 6, the square root of 7n squared over the square root, over 9m squared. Let's write the radicand as two separate radicals. The square root of 7n squared all over the square root of 9m squared. Now, that denominator, you can't take the square root because 9 is a perfect square and m squared is a perfect square. That will give us 3m. But our numerator, 7 is not a perfect square, but n squared is. So we're going to take the square root of this n squared. And when you take the square root of a factor that's a perfect square, tell me the root, but you're going to bring the root on the outside of the radical, in front of the radical. So the square root of n squared is n. So we bring that n on the outside. The 7 will stay under the radical sign because it's not a perfect square. So our solution is n in the numerator times the square root of 7 all over 3m. Number 7, We have the square root of x to the ninth, y to the 11th, all over the square root of xy. So this particular example is already written as two separate radicals, but there's really nothing that we can do at this point. I will say this, there are other ways to looking at this, but we haven't talked about the concept of rationalizing a denominator just yet, so I'm not going to introduce it here. But what we're going to do is write the radicand as one separate radical, excuse me, as one fraction. Okay, so we're going to take the radicand as write it as one fraction. We have x to the ninth, y to the 11th, all over xy. So at this moment, or this question, if we didn't have the radical there and I told you to simplify this fraction, you should be able to do that for me. Remember we talked about when we were working with exponents, we had the quotient rule. Okay, so this is what we're going to do. We're going to use the quotient rule where we're going to subtract. So where do you have the greatest amount of x's that you see? We have it in the numerator. So we're going to subtract an x from out of x to the ninth. We have x to the eighth power. Then where do you, for your base y, where do you have the greatest amount of y's? That's in the numerator. We're going to subtract a y from out of y to the 11th. We have y to the 10th. So now under the radical sign, we have the square root of x to the 8th, y to the 10th. Okay. And then x to the 8th, y to the 10th, they are perfect squares because 8 and 10 is a multiple of 2. So our solution is x to the 4th power, y to the 5th power. And that will be our solution. When your answers are perfect squares such as this, the factors are, when it's a perfect square, we don't need the radical anymore. Okay, whereas in the previous example, that 7 was not a perfect square, it needed to stay under the radical. Last two examples here with dividing. We have the fourth root of x over 256. Let's write the radicand as two separate radicals. You have here the fourth root of x over the fourth root of 256. The numerator, the fourth root of x, there's really nothing that we can do about that other than just say the fourth root of x. But the fourth root of 256, can you find 4 identical factors that will give you 256? That will be 4 because 4 times 4 times 4 times 4, that is 256. And if you're not sure, you can use your calculator. And then we will put in 4, press that accent key. This is the accent key to tell the calculator that your index is 4. So second and the accent key, and then enter 256 and press the enter key, and we have 4. Last example, we have the cube root of 3 over 8. Let's write 3 over 8 as two separate radicals. We have the cube root of 3 over the cube root of 8. Now, the numerator, 3 is not a perfect cube, not 1 plus 1 plus 1. But remember, it must be factors. So the numerator will stay as the radical. But we can find the cube root of 8. What are 3 identical factors? When we multiply it, will give us 8, and that is 2. So our solution is the cube root of 3 all over 2.